Okay, hello everybody. This is going to be a little bit different. Um, we're not in our class, but hopefully this will be just as easy for you to follow because you can just look at the notes and pay attention to what I'm writing. Feel free to pause and go back and rewatch things, or pause so you can write things down, pause so you can try things on your own, all of that. Okay, so before we left for spring break, we finished up chapter 8, which was our last hypothesis testing chapter. So we're looking at chapter 9 now, which is all about correlation and linear regression and everything like that. So a correlation is just a relationship between two things. So generally we talk about it on a scatter plot, which is what you see down here. So we've got two variables, generally an x and a y. We use our ordered pairs to represent it. Sometimes it'll tell you which data is your x values, which data is your y's. It doesn't really matter which one is which. If it doesn't tell you that, you can kind of pick that on your own. But your x values are your independent values or your explanatory values or variables. Y is your dependent or response values or variables. So we have four types of correlation. We have a negative linear correlation, so that's generally when all of our data is going down to the right, so it has a negative slope. It doesn't have to be perfect. It just has to generally follow that. We also have a positive linear correlation, which goes up to the right, so it essentially is going to have a positive slope. No correlation is when it doesn't have any sort of pattern to it. So like if we look at all of these points here, they're not going up to the right or down to the right, they're just kind of scattered. And then our last type of correlation is called nonlinear correlation. So that's going to be when your data generally follows some sort of pattern, some sort of shape, but it's not a straight line. So in this case, we have data that seems to basically form a U shape, which would make it a quadratic correlation. So in this first example, a director of alumni affairs at a small college wants to determine whether there is a linear relationship between the number of years alumni have been out of school and their annual contributions in thousands of dollars. So like when we look at these values down here, the 12.5, 8.7, all those are in thousands. So that's $12,500, $8,700, that sort of thing. The data shown in the table display in a scatter plot describe the correlation. So our years are going to be like our x values, our contributions are going to be our y values. It doesn't really matter what you make your increments go up by. That's kind of up to you. We have everything from 1 all the way up to 30 for our x's. So I'm just going to go up by 5s here. You could go up by 2s or 3s or 4s, whatever you want is fine. And then my contributions, so I've got from about 2.7 to almost 15. So I'm just going to go by 3s. one above there just so that we have some extra room. So we're just plotting that data. So after 1 year, a person contributed 12,500. 10 years, they contributed 8.7. These points don't have to be perfect. We're just looking for like general area. 5 years was 14.6. 15 was 5.2. 3, 9.9. 24 and 3.1, and 30 and 2.7. So that data is pretty spread out, but you can kind of tell like the closer to graduation that you are, the higher those donation amounts are. The farther it's been since you've graduated, the lower those money amounts get. So this is going to have a negative correlation. Okay, so remember, we're just looking at, is that going generally in some sort of pattern? Is it generally going up? Is it generally going down? Things like that. If it's not doing any of that, it's fine. Okay, so I would really like, okay, so I would really like it if number 2, you guys took a second to try this one on your own. You're going to do the same thing. So a researcher conducts a study to determine whether there's a linear relationship between a person's height in inches and their pulse rate in beats per minute. The data shown in the table, display it in a scatter plot, and describe the correlation. So you're just going to create a scatter plot just like we did in number 1. Your increments on your x and y variables really don't matter. That's up to you. But go ahead and pause this and just see what you come up with before you continue watching what I've done. Oop. Sorry about that. Okay. So I am going to have my heights go up by 4s or so. But remember, we can put that break in our graph so that we don't have to start at 0. Our smallest height is about 62 inches. So I'm going to start at 60. And then go up by 4s from there. And I'm going to do the same thing on my y-axis. So my x was my height, my y is my pulse rates. I'm gonna go by 10s on this one. So I'm gonna start at 65. Okay, so I've got 68 and 90, 72 and 85, 65 and 88, 70 and 100, 62 and 105, 75 and 98, 78, 70, 64 and 65, and then 68 and 72. So when you look at this graph, there's not really, it's not really going down and it's not really going up. It's just kind of all scattered around, especially with these 2 points adding into that kind of skews the rest of the data. But I would say that this would be a no correlation graph. Okay, so the one thing about using scatter plots to interpret correlation is it makes it pretty subjective. Ethan might think that it's a really strong negative correlation, but Braden might think it's not that strong. It's negative, but it's not really that strong. So it's kind of subjective. So what we can calculate is called the correlation coefficient. You hopefully did this in Algebra 2, but you probably did it on your calculator in Algebra 2 or Algebra 1. We are doing it by hand, which can be a little bit annoying, but really it's just a matter of plugging things into the formula. So our correlation coefficient is represented by the letter R. It measures the strength and the direction of the linear relationship between your two variables. So if we were to find that value, what we would do is we would take our n value, which is just the pairs of data, and then we'd multiply that by the sum of x times y. Then we're going to subtract the sum of x times the sum of y. And now in our denominator here, we have 2 square roots. So be careful when you're putting that into your calculator, because it's this first square root where we have n times the sum of x squared minus the sum of x all squared times the square root of n times the sum of y squared minus the sum of y all squared. So this is 2 different square roots here that are being multiplied together. So as you put that in your calculator, you want to be mindful of that so that you don't end up with a wrong value. Your correlation values can run anywhere from -1 to +1. So if it's a negative number, that means you have a negative correlation. If it's a positive number, you're going to have a positive correlation. But if it's not -1 or +1, it's a decimal, less than 1. Okay, so you're not ever going to have 1.25 or -1.25 or anything like that. It's always going to be in between -1 and +1. So the stronger the correlation, the closer it's going to be to 1 or -1. And remember, if it's close to +1, it's because it has a positive correlation. If it's close to -1, it's because it has a negative correlation. When there's no correlation, no linear correlation, R is going to be really close or equal to 0. So just keep in mind that your data can have no linear correlation, but can still have a different type of correlation. So it could be quadratic or exponential or something like that. So your R value could be really close to 0, but it might still have a correlation that's not linear. So a couple of guidelines for calculating a correlation coefficient. You're going to find the sum of your x values first. Then you're going to find the sum of your y values. You're going to multiply your x and y values together. Make sure it's the corresponding ones. You don't want to just pick 2 to multiply. And then you're going to find the sum of that. So you're going to add those up. You're going to square each x value and add those. Square each y value, add those. And then you're going to plug all those 5 values that you found to calculate your R value. In number 3, we're going to go ahead and calculate our correlation coefficient. So when you're doing this, you want to make sure that you're adding your sums appropriately. So we're taking that same data from number 1, the years out of college and the money contributions that those alumni are giving back. So our years out is still going to be our x values. money contributions is still going to be our y values. So we have to have the sum of our x's. So I'm going to go ahead and add those up. So 1 plus 10 plus 5 plus 15, 3, 24, and 30 gives me a sum of 88. I'm going to add my y's. 12.5 plus 8.7, 14.6, 5.2, 9.9, 3.1, and 2.7 gives me a sum of my y's of 56.7. Now I'm just going to add rows down here, x times y. So I'm just multiplying each data pair. So 1 times 12.5, 10 times 8.7, 5 times 14.6, 15 times 5.2, 3 times 9.9, 24 times 3.1, 30 times 2.7, and then we're going to add all of those together, which is going to give us 435.6. And then I'm going to do my x squareds. So 1 squared is just 1, 10 squared is 100, 5 squared, 15 squared, 3 squared, 24 squared, and 30 squared. I'm going to add those up, which is going to give me 1,836. And then I'm going to square my y values. 12.5 squared, 8.7 squared, 14.6 squared, 5.2 squared, 9.9 squared, 3.1 squared, and 2.7 squared. So once you have all of those values, we're going to add all of our y squareds up, which gives us 587.05. Okay, so once we have all of our values, it is just a matter of plugging things into our formula and working it out. So we have 1, 2, 3, 4, 5, 6, 7 data pairs. So we're going to have an n value of 7. So when we plug in for r, it's n times x, the sum of xy, which was 435.6, minus the sum of x times the sum of y, all over the square root of n times my x squared, the sum of my x squared, minus the sum of my x's squared, and then times the same thing just with my y's. So this the square root of n times the sum of my y squared minus the sum of my y's squared. So 7 times 587.05 minus 56.7 squared. Okay, so everything's plugged in. So what we're going to do is we're going to type that into the calculator. Be careful if you plug it in all at once. My suggestion would be to put parentheses all around this first one, all around this second one, and all around the entire numerator so that it doesn't mess it up in your calculator. And then put parentheses around the entire denominator. You don't have to put them in around the individual square roots. You just have to make sure that the square roots are going to do it in the order you want. The way I have it written right now, it should work out just fine. And when you plug all that into your calculator, I'm just going to round to 2 decimals. You should get about negative 0.91, which is a strong negative correlation. Okay, so with number 4, I would encourage you to do the same thing and pause the video and try to find the correlation coefficient on your own. So you have average salaries, not average salaries. You have salaries for different MLB teams in millions of dollars and their average attendance for just the home games. So find that correlation coefficient and then interpret your results. So do the same thing that we did in number 3, just with smaller data. Keep in mind these numbers are very large to start with. So when you're adding them together and squaring them and then adding them together, you're going to get fairly large numbers. So go ahead and start doing that. Pause it on your and do it on your own. I'm going to go ahead and start doing this now. So when we are finding all of this data, all this information, we want to add our x's. Our salary is going to be our x's. Our attendance is going to be our y's. So bear with me for a second while I type these things into the calculator. Okay, so when I add my y's and my x's, the sum of my x's, I'm going to get 500.4. When I add my y's, I'm going to get 156,528. For x times y, this is a really big number, so hopefully you didn't panic and think that you had the wrong number. 16297926.8. So 16,297,926.8. The sum of x squared is 56,862.82, and the sum of y squared is super large, 500, 139, 2850. So 5,001,392,850. Okay, so when these numbers are huge. When we plug all of these into our formula for R, so remember, our formula for R is N, which is how many data pairs we have, which in this case is 5, times the sum of X times Y, minus the sum of X times the sum of Y, divided by our first square root, which is our N value, times the sum of X squared minus the sum of X squared times our second square root, our N value, times Y squared minus the sum of Y squared. So when we type this all into our calculator, I'm going to do this piece by piece so that I know I don't forget a parenthesis or anything like that. Which gives me a correlation of about 0.76. So it's positive. It's a positive 0.76, so it's a positive correlation. It's not super strong. I'd say it's probably pretty moderate. So I'm going to say it's a positive moderate correlation. Generally speaking, 0.5, that, whether it's positive or negative, it's halfway. I wouldn't really call that strong or moderate. It's just it would just be positive. If it was less than 0.5, it would be a weaker correlation. If it's between 0.5 and if it's between probably 0.6 and 0.8-ish, it would be moderate. Anything above 0.8 is strong, but again, that's kind of up to your interpretation of what would be stronger and what wouldn't be. So as long as you're not telling me that a correlation of 0.5 is a strong correlation, it's probably going to be fine. But generally speaking, 0.8, 0.85 and above is going to be strong. Somewhere around 0.6 to 0.8, 0.85 is going to be moderate. Less than half is going to be weak. Okay, so once we find our correlation coefficient, we want to determine if there's enough evidence to decide that the population correlation coefficient P is significant. In order to do that, we the absolute value essentially has to be close to 1. So it really does have to deal with what our R value is, but that R value is, and if it's significant, is also going to depend on if it is a larger sample or a smaller sample. If it's a smaller sample, it can still be significant depending on having a lower R value, or same thing if it's a bigger sample size. So it all kind of just is dependent upon what our sample size is and what our R value is and all of that. So when we look at that, we're essentially going to look at table 11 in the back of our book. So the guidelines for using that table, we're going to determine the number of pairs of data in our sample. So we're going to make sure we know what n is, which we should know if we ourselves found our R value. We're going to specify that level of significance, which it will tell you. We're going to decide whether the correlation is significant. So if the absolute value of R is greater than the critical value, it's significant. If it's not greater than the critical value, then there's not enough evidence to conclude that the correlation is significant. And then you just interpret in context of the original claim. So in number 5, we are looking back at that information from numbers 1 and 3. I didn't add the table back in because all we really need for this is the R value that we found and the alpha that it wants us to use. So it's the number of years out of school and the annual contribution data. We found that R value to be negative 0.91. So it was a pretty strong correlation, and it was just negative. So we want to know if it's significant at 0.01. So we're going to say, okay, well, my absolute value of R is going to be positive 0.91, because we're always comparing it to that absolute value, because the table that's built in is always positive. So table 11 is on page A26 in your book. It actually has 2 tables on it. It has table 10 and table 11. We're specifically only looking at table 11 right now. So basically what we're going to do is we're going to say, okay, my n value was 7 because I had 7 data pairs. My alpha is 0.01. So on the table, I'm going to go over to whatever that alpha is. In this case, we only have options of 0.05 and 0.01 for this, which is fine. So we're going over to 0.01 and down to that n value. No degree of freedom, just n. So when we look at that critical value is 0.875. So now we just have to say, okay, is the absolute value of R greater than my critical value? So is 0.91 greater than 0.875? Yeah. Okay, so that's a true statement. Since the absolute value of R is greater than our critical value, our correlation is significant. And then remember to interpret. So your interpretation is really going to be the same, essentially, that it was in the last 2 chapters. So we have enough evidence. The one thing you do want to include is your level of significance. So enough evidence at a 1% level of significance or level of confidence, it really doesn't matter, to conclude that there is significant linear correlation between the number of years out of school and money contributions to the school. Okay, so I don't want you to get it hung up on the interpretation because it really very much is the same that we did in the last two chapters. It's just a matter of we're determining, is there significant linear correlation or not. So instead of saying we can reject or fail to reject, we're just saying, yeah, this is significant correlation. We're good. Now, you might notice in this section that there is a hypothesis test that we can also do. We're not going to worry about that in this one just because it's not significant enough to spend our time doing it, especially since we're not at school where I can like sit right next to you and walk you through it. But I'll post this on the Google Docs page as well. But since you are listening to this, the 9.1 assignment starts on page 481. So, page 481. And we're looking at numbers 2 through... Let me make sure that this is the right number. 2 through 34 even. What I will probably have you guys do is just take a picture of your work and then email it to me or send it to me on Google Docs, whatever is convenient for you. That really doesn't matter to me. Make sure you show your work. Don't just write like it's significant correlation or it's not significant correlation, like many of you did in the last two chapters, because that didn't really work out in your favor when it came time for the test or that project at the end of the 9 weeks. So show your work on it. If you don't show your work on it, I'm going to give you a 0. Okay? If you have questions, email me, request a Google Meet, whatever is fine, and I'd be happy to walk you through anything you didn't understand.